Okay, hello everyone and welcome to another video. You've probably seen I've already posted a video up on statistics. There'll be more of those coming soon, but this is the very last sort of differential calculus video that I'll be doing. And it's looking at one of the SACE 2008 exam questions. So we'll be going through this and before we move into statistics, just to get an idea of what kind of questions we might actually face in an exam situation. So I'm looking at question 12 here, and it's giving us a graph. It's an implicit relationship because we have x's and y's on the same side of the equation, and we've also got a line which where x equals k, and it's denoted by pq here. And in this particular example, k is equal to 2, so that line just goes where x equals 2 because x equals k. Okay, nice and simple. So we've got this graph here and we can see the implicit relationship. What it asks us is a series of questions regarding this. And the first one is very simple. It is a 1-mark problem and it asks us to show where k is equal to -3. Okay, so for 1 mark, draw on the graph above where k equals -3. Okay, and from the question, we can see that the line PQ is given by x equals k. So therefore, where k equals -3, it's the same as just having a line where x is equal to -3. And because it's x equals something, we know it's going to be a horizontal line. So if we were to draw this on the graph, and I know this is a pretty miniature graph, but it would just pass through -3. It would be, it'd be a vertical line, not a horizontal line, a vertical line going through -3. And that's the case because, of course, it's going to go straight through, and all values on that line is where x is equal to -3. Okay, so that was pretty easy for 1 mark. We just saw -3 as x, and we just drew a line through it. Nice and simple. But it gets a little bit more difficult now when we start looking at the next question, where it says calculate the coordinates of P and Q for the case where k equals 1. So we need to find what these coordinate values are when k equals positive 1. So when k equals 1. So what we have to do here is, because k equals x, we know that this is when x equals 1. Okay, so because x equals 1, we take our implicit relationship and we substitute in 1. So we get x squared, take xy plus y squared equals 12, and therefore 1, because 1 squared, 1 times 1 is going to be 1, take 1 lot of y, again I'm just putting in 1 wherever there's x here, plus y squared equals 12. Okay, and so from this, we can see that this would also be written as 1 take y plus y squared equals 12, because 1y can be the same as y. Okay, so from that we need to be able to get this into the form of a quadratic in order to solve for the two y variables, obviously p and q, and then from that, what we can do is we can say, well, we can get rid of 1 and bring it to the other side for the purpose of algebra, so it's going to be -y plus y squared equals 12 take 1, because it's positive 1 here, so it's going to be negative on the other side, and therefore what we do is we have -y plus y squared equals 11, because 12 take 1 is equal to 11. Now from this, what we do is we bring this to the other side, and because it's positive there, it's going to be negative on the other side. You probably could have worked out that it's going to be 11 just by looking at that one there, and you just could have jumped ahead and say, oh, it's going to be -11. It's up to you. I'm just running through step by step. Generally, I like getting my constants on one side of the equation, simplifying that down, and then bringing it back to the side which has the pronumerals. But again, you can do it however you want. This is just how I would set it out. And then what we do is, of course, we would have y squared. I'm putting the highest power first. So y squared, the highest degree of the polynomial. Take y, and then it's going to be take 11, because it's positive there, so it's going to be negative there, and all of that equals 0. So now we can use the quadratic formula in order to solve for the two y values that we'll end up getting, and this will give us the y coordinates of p and q. Now we know that both p and q lie on the line 2 there. So if they lie on the line 2, then what we're going to end up with is both the x coordinates are on line 2, so therefore both the different y coordinates are going to be a result of this. Okay, so now that we have that, what we can move on to do next is say, therefore, a equals 1, and that's just a coefficient of the first term. Imagine this is a take bx take c. So a equals 1, because that's a coefficient there. Then b equals -1, and c equals -11. Now from this, we can actually solve using the quadratic formula, as I said before. So the quadratic formula is given by y equals -b plus or minus the square root of b squared take 4ac on 2a. And we just substitute in, so therefore y equals -b, so -1, the negative version of that's going to be 1, plus or minus the square root of, and then we have b squared, so it would be just 1 squared, which is going to be 1. Take 4 lots of a, and a we know is going to be equal to 1, and we know that c is going to be equal to 11. -11. And that's all going to be over 2 lots of a, which is just going to be over 2. So what we get is we get the y equals 1 plus or minus, and let's simplify what's under the square root of the bracket there. So we have 1 take, and 11 times 4 is going to be -44 times... no, sorry, let me start that again. -11 times 1 is going to be -11, and you times that by -4, and you're going to get +44, because a negative and a negative make a positive. So that's going to be -44, 1 take -44, double negative, so it's going to be over square root 45, and that over 2. So now we're going to get our y coordinates. Now in order to do this, I might just rub out a bit of space here, because of course I'm probably writing really slanty, given the angle that I am relative to the board, but that's okay. We've got what the y coordinate is, and we're able to solve through it now. So we can just go, therefore, y1 is going to equal 1 plus the square root of 45, because again, it's plus and minus over 2. And therefore, y2 is going to equal 1 take the square root of 45 on 2. And now I need to think about our 2 coordinates. And we know that both of them are going to have x of 2, because they're on the line k equals 2, and k is the same as x. So it's going to be 2, and now I need to think about which one's p and which one's q. So we've got p and we've got q, and let's think about it. P is up here, it's in the positive quadrant. We have positive x and positive y, so we're going to need a positive y. So therefore we'll be looking at y1 for p, because it's 1 plus the square root of 45. And you can tell the square root of 45, if you were just to have an estimate of it, it would be somewhere between 6 and 7, of course. So from that, you know, it's like having 1 plus 6.5. I know it's more than that, but it's an example of having that. 1 plus 6.7 probably, over 2. And you know you're going to get a positive result there. And because P is going to have a positive y value, and Q is going to have a negative y value on the Cartesian plane, we know that y1 is going to be the y coordinate for P. 1 plus the square root of 45 on 2. And then y2 is obviously going to be the other one, because it's going to be a negative coordinate, so it's going to be the q value, the y coordinate for q. 1 take the square root of 45 over 2. Excellent, and we solved that question there, 2 marks, and we get to move on to the next question, and that is show that y equals, the dy over dx of this implicit relationship here is equal to, and I'll just write it up here on the board so we're able to refer back to it, but it asks us to show the steps in implicit differentiation. Okay, so we have x squared take xy plus y squared equals 12, and it says show that the dy over dx of that is going to be equal to, and it gives it as y take 2x on 2y take x. Okay, so we have to show that. Well, let's think about it. Okay, we have x values and y values. We have a product rule here because we have two terms multiplied by each other. And of course, when we do implicit differentiation, as I've mentioned in my previous video, you always go through it one term at a time. So let's just start down here. And again, what we have in the dotted box there is what we need to show. So we have x squared. So that's going to be 2x when we differentiate it, because we bring the power down to the position of the coefficient, and that's the product of the coefficient and the power, which is going to be 2 times 1, which is going to make 2x, and then we subtract 1 from the power, so it's just going to be 2x. Now what we do is we use product rule here. So we have our f of x and our g of x, and what we do is we take the f prime of x first. So it's going to be take, and the derivative of x is of course going to be 1, because there's an imaginary coefficient there, and when we subtract 1 from the exponent, it's going to be x to the power of 0, and anything to the power of 0 is going to be 1. So we have take 1 lot of y, because we have the second term as is, and then it's take, and then we have the first term as is, and then multiplied by the derivative of y. And with implicit differentiation, if you haven't seen my video already, you should know that y prime is dy over dx, because we're giving respect to x when we're implicitly differentiating. So it's x times dy dx, and then it's plus, and then we bring the 2 of the exponent down and multiply it by a coefficient, so we get 2y times by dy over dx. And that's all equal to 0, because the derivative of a constant is 0 on the end there. And what we do is we gather up all the terms that have dy dx in it, and we put it out the front. So we have the dy over dx of, and then we have a bracket, and let's see, we've got an x there, and we've got, and this can just be take y there, I'll get rid of the 1 there, but that won't help us now. So it's x plus 2y, because of course 2y is left over, because that's multiplied by dy dx, because we differentiated a y term in order to get that, but we have that equaling, and then any terms that don't have a dy dx, we just inverse the operation because we bring them to the RHS. So that's 2x there, so it's going to be negative 2x, and then we also have take y, so it's going to be positive y. And therefore, the dy over dx is, and we bring this bracketed term here from the LHS of the numerator to the RHS denominator. And again, we've got to show that it fits this format. So because this is positive y here, we can put y out the front, and that's take 2x. And again, we bring this from the we bring that from the denominator there, and what we can see already is that I've made a small mistake here. I forgot the negative sign, so I need to remember to keep the negative sign in there. That's a good thing about the show that questions. You can always see if you've been muddled up with the sign somewhere. And so we have negative x plus 2y. That's the same as having 2y take x, because that's positive, that's negative. So we're just changing the order and that sign, and hence we have shown that. And my writing is obviously very slanty, so I'm just going to have another go at ensuring that you were able to see what I just wrote. So hopefully that's all good now. Sorry for my slanty writing, I apologise, but we've answered that question, and that question, again, was worth 3 marks actually. So that's implicit differentiation there. Now what we need to do is we need to answer the rest of the question, and this is 6 marks worth that we have for the rest of the question. So again, it's broken down into 3 parts, part D of the question, and the first part asks us to do, in fact I'll just check the time. Yep, I'll probably actually cut it here, because in that case I'll do it as a 2-part video, because I don't want to make it go for too long, and I want to be able to upload directly off my iPhone, so I can only keep it at 15 minutes. But just have in mind what we've done so far. Question 12 of the SACE 2008 Math Studies exam, A, B and C. When I get back, we'll be doing part D in the next video, so make sure you watch that. Thank you.